Okay, so in this video, we want to look at this concept of continuity. What makes a function continuous? And it's definitely a great follow-up to limits, because the definition of something that is continuous involves a limit. And so, I'll present a very formal definition of continuity, and then also a more kind of intuitive or just kind of like a graphical representation of things that are continuous. So formal definition of continuity is we'd say a function is continuous at point A. So a function f of x is continuous at point A if the following three things hold. If one, the limit as x approaches a from the right of f of x equals some c value. 2, the limit as x approaches a from the left of some of the function equals the c value. And 3, f of a does equal c. And so, those three pieces is something that we're going to rigorously prove next year in calculus. And for us, the idea of a limit or of something being continuous is that if you have a graph and here's like your a value and here's your c value, which is a y value. And so this idea of the limit as x approaches a from the right side, so we're going in this direction, as x approaches a from the left side, and actually at f of a, everything equals to that one point. And then we say the function is continuous at that point. And if a function is continuous at every single point, then we say the function is continuous. Now, we'll talk about what algebraically could give rise to something that's discontinuous, but just to get another picture of what's happening, like there are different kinds or things that can happen in your graph to make something discontinuous. And so one of the things you can have is a hole. So like this one right here, like this idea of a hole, and I know this isn't in our notes, but something that you might want to write down and take notes on, just because it is important. So a hole doesn't, like the limit from the left equals limit from the right. So the limit definitely exists, but the function value is way up here. So if we think about those three components, does the limit from the left equal the limit from the right equal the function value? Only 2 of the 3 do. So this hole, this hole here is what we call a removable type. It's a removable discontinuity, and you don't have to worry too much about the different kinds, like is it removable or not removable discontinuity. But again, the idea is that the limit from the left, limit from the right, and the function value, all 3 don't equal each other. So, but it is certainly possible to assign one value to fill that hole. And so, if you could assign it by one value, if you can assign that discontinuity by one thing, that's what makes it that's what makes it removable. If you can't assign it by one point, then we call that non-removable. So the rest are examples of non-removable. So this next one is a jump, and usually they're a little bit more clear. Like one side might be filled in, and one side might be open. So this idea of a jump discontinuity happens when a piecewise function doesn't quite line up. And again, 2 of the 3 components of what makes something continuous fail. Like maybe the limit from the left equals the function value, but the limit from the right is something completely different, right? Limit from the left and the function value, if that's filled in, are the same, but the limit from the right is way up here. So this idea of a jump is non-removable. Okay. So I can't assign one value. I mean, you can't just make this like super big dot to connect the two. It doesn't work like that. Another type of non-removable is approaching an asymptote. Okay. So here, the limit from the left does in fact equal the limit from the right. They're both infinity, right? So having a limit of quote unquote infinity still describes the behavior of our function, but it's not defined at that point. So again, 2 of the 3 components of the definition of a continuity are work, but one fails. And like an asymptote is also non-removable. And then this last one is an oscillation, and it rarely happens, but it's kind of an interesting sort of concept. So oscillation is also non-removable, but this function I have here is sine of 1 over x, and the limit as x approaches 0 of this function basically oscillates to like forever. And the closer you get to 0, the faster, the more frequent those waves are. Because if you think about what's happening as you get closer to 0, like as this gets smaller, overall the number gets very large, right? And so and there's no end to the sine graph. It just keeps bouncing back and forth between 1 and -1, 1 and -1, 1 and -1. So it's like this weird oscillation that the closer you get to 0, the more like these waves get closer and closer and closer and closer and closer and closer together. The thing is, you never get to 0 because I can't let x actually equal 0 because you would have been dividing by 0, and that's a undefined point. So kind of what you need to take from this is that like a hole is one kind of discontinuity, an asymptote. Oh, sorry, here it is. An asymptote is another discontinuity, and then a jump when two piecewise functions don't line up. So algebraically, we've seen some of these things already happen. A lot of it happens when you divide by 0. And if you're not dividing by 0, if things are smooth and connected, then your function would be continuous. And so that's another kind of intuitive definition of continuity. I like to call it smooth and connected. If you could draw it without lifting up your pencil, then you know you're continuous. If I'm drawing a function and I have to lift up my pencil to come up here and then continue my drawing, it clearly is not continuous. Now, if I don't see a graph and I just have this equation, it's just a linear equation. There's nothing that mathematically I can't do. It's just you're not dividing by 0 or square rooting negatives. You just have an equation you just have an equation of 2x minus 9. So there are no asymptotes or jumps or holes or oscillations. So where is this continuous? Everywhere, right? And a lot of functions that we've studied that are like polynomial are going to be continuous everywhere. Where we start to get discontinuities is where we divide by 0. And so if I think about here, it's definitely not continuous at x equals -2. So it's discontinuous at x equals -2. Now, we saw last semester that when you divide by 0, you either get a hole or you get an asymptote. There it is, depending on if you can cross out a factor. And if you notice in this one, I can actually cross out a factor. So if you reduce this polynomial in the numerator by factoring, and you remove this factor here, we are left with a linear function with a hole. So if I were to have graphed y equals x minus 2, but not let x equal -2 because it was an undefined point, I would get the graph of this function. And at -2, if I follow that line, it would have been at -4. There would have been a hole. And of course, I should probably, there we go, raise that up. And that would be the one point that is discontinuous. So I would have this line going here. There'd be a hole, so I have to pick up my pencil, and then I continue in that fashion. So there's an example of a discontinuity that is a point. And then, excuse me, number 3 is trying to make this function continuous, like trying to fill that hole, if you will. So one thing I'm noticing on number 3 is that I can still factor that, right? So if I were to have factored the top to get x plus 6 and x minus 6, I would notice that I have this factor that I can remove. And again, that's kind of this idea of removing that factor. Part of the reason why we call this removable discontinuity, that's going to give rise to that hole. So if I take a look here, I've removed that. So the reduced value is x plus 6 as long as x is not 6, because remember, we removed that point. So what does that graph look like? Well, It's a linear function. It has an intercept of 6, 1, 2, 3, 4, 5, 6, and a slope of 1. And so, I would draw this line, except for at one point when x is 6, I have to put a hole there, right? Because I had crossed out 6. So 6 comma something represents that particular point. And, if you remember from last semester, we can actually find that y value. We can find what should that y value be by simply taking 6, that factor we crossed out, and putting into the reduced equation. So if I do that, if I put that into the reduced equation, 6 plus 6, oh, that's 12. That's the y value. So geographically, I know that y value is 12. Well, that's exactly what I want to assign B, because I can pick one point. If I can pick any point to fill that hole, obviously I want to pick the y value, the y coordinate. So choose B to be 12. And if I choose B to be 12, if I choose that value to be 12 when x is 6, that would fill that hole. Okay, so again, trying to maybe associate just the terminology of what it means to be continuous versus discontinuous with actually concepts we saw last semester, right? When you have a hole, it is, it's a discontinuity, but it's removable. You could take one value, assign it to fit the y value that's missing, and it would make the function continuous. Another type of discontinuity is the asymptote, which would happen if you were dividing by 0 and you couldn't cross out a factor. And I don't know if I have one of those readily on this particular note sheet, but anytime that you are dividing by 0 where you can't cross something out. So, like, for example, this right here, it says consider this function 2 over x plus 1. Clearly, x plus 1, would equal 0 when x is equal to -1. So that's an issue, right? So it's discontinuous at -1 because at -1, since nothing crossed out, there would actually have been a vertical asymptote. So, okay, I think it's a good start for this first video. And then the next video, we'll look at some more of those piecewise functions and start analyzing what happens if those two sides don't line up.